Hello, this is my presentation for Physics Lab 1, focusing on constant velocity motion. I'll be discussing my analysis of an object moving at a steady pace and comparing those observations to my computational model. Fundamental principles. So, this lab analyzes the motion of a cart moving in one direction at a constant velocity. When an object is in constant velocity, its acceleration is 0, which basically allows us to simplify a primary equation being the velocity update and position update formula. So VF equals VI plus AT, and RF equals RI plus VT. And basically, since acceleration is 0, we don't need the half AT squared version of our position formula. All right, so our goals. Basically, we wanted to measure the motion of an object. In this case, it was a cart, and observe its position changing at a constant rate. So that's what we expect. Number 2, we're going to compare the actual motion to a computational prediction using ClosScript. So to model this effectively, I made several key assumptions. We had to assume that the velocity remained perfectly constant, and we chose to ignore air resistance and any other movement on any axes. And remember, going back to F equals ma, if v equals 0, then a will equal 0 because acceleration is just the derivative of velocity. So this is all according to our velocity update formula. All right, so then on our tracker, you can see here, we set the y-axis as the one for the movement, and it's a little bit laggy, but it's basically showing how we tracked each point every 0.033 seconds. And we used our meter stick as a reference point. But in a real-world situation, it's quite difficult to determine exactly how many forces we're adding together to give a net zero force, and how many forces there are. There's gravity, normal force, drag force, friction force. But basically, if we want to visualize this, how does F net equal 0 in this case? This is because we're assuming no friction force, and the normal and gravity forces both cancel out because they're in equal and opposite directions. And then the reason it's moving is because we have the applied force at the beginning, which is the push. Then the experimental conditions. We use a tracker to analyze the video. Our system is the cart, and the surroundings are the surface and air. We set the origin at the initial point of motion, use a meter stick for the scale. For the first 2 time steps after it's pushed, we calculate the initial velocity of 0.448 meters per second, give or take. And you can see how we did the calculations here using the delta y over delta t. Then the code analysis, you basically set the initial position and velocity. As you can see here, using the .pos and .vel. And then we set the delta t at a 0.033, which is just what the tracker data did. And then the code analysis, we have a while loop with a t less than 2.7 because that's how long it's going to run for. And then we set f net to 0, which is simulating the ideal constant velocity. Then each iteration, the code updates the velocity and it predicts the trajectory. Using right here, it adds incrementally times the delta t, and then it prints it out. And then you can actually see it running if we go here. So there we go. That's our code. Experimental data versus a model. So the red is predicted, observed is blue. The red is perfectly straight because that's our position equals v times t. And since the velocity is staying the exact same because there's no external force, it's straight. Meanwhile, in the real world, we have friction, air resistance, and other things acting, so it falls slightly behind as time goes on because the ideal model does not account for that. What if we flip the axes? So basically, if you swap the positive y and negative y axes, the magnitude of the velocity would be the exact same, but the direction would be negative, so you'll just invert it over the x-axis. So what does this mean? One of our key requirements is discussing the forces on our system, and while Newton's second law tells us the sum of all pushes and pulls that equals 0, it doesn't give us the individual forces, so no, we cannot identify every individual force at play. Thank you very much. That's been the end of my presentation.